Hey everyone, let's jump into 6.7, which is on harmonic motion, just some examples or some applications of the sine and cosine waves. So we have a situation here where there's a weight attached to the end of a spring, and then that weight is pulled down and is put in motion. And so we have three positions as that thing oscillates up and down. We have A, where it's at rest, right? And then it was pulled down and then it hits its maximum. Okay. So the place that's in the middle right there, we're calling that the equilibrium position. Okay. And then you have a minimum B and a maximum C. Okay. And it just continues to oscillate. Um, in that situation, you can model the motion of the weight using either sine or cosine, right? And they're of this form here. Okay. Now, which one you choose depends on your starting position. And we'll get more into that with some examples. But if your starting position is either at the minimum or the maximum, that's going to be a cosine example, right? Because if you think about the cosine graph, it starts at the top or the bottom. Whereas if your starting position is that equilibrium position in the middle, that's the sine, right? Because sine starts in the middle and then rises, falls, and then goes back to the middle. Okay. And then we have three key terms we'll be using in this section, two of which we've already seen. Amplitude is the same. That's going to be the distance the object is pulled down in this case. The period is the 2 pi over omega. We're using omega instead of b here. Fits better with the examples, but it's the same formula. And in these examples, think of the period. This is the length of time it takes for one full oscillation. Okay. So as this spring is bouncing up and down, if it goes one full oscillation, however long that takes, the time, that's the period. Okay. Whereas the frequency, which is known as the reciprocal of the period, that's the number of oscillations per unit time. All right. So how many times is it oscillating per second or per minute or per hour, or whatever it is you're talking about. Okay, so that's the introduction. Let's jump into an example and try these out. So here we have a situation where you have an object attached to the coiled spring. It's pulled down a distance of 5 inches and then released. The time for one complete oscillation is 4 seconds. It might be worth looking really quickly at some animation because this is motion. So let's, I'm going to share my desktop real quick. And if you see here, this is exactly what we're talking about, right? So if we just look at this spring oscillating, or this weight oscillating up and down at the end of a spring, and then we translate that to a sine wave, there it is, right? Where the x-axis is actually the time and the y-axis is the position, okay? You could also think of this as on a circle, right? Where the angle is the time and then the position is the y value, right? So that's a useful little animation to help get your head around what we're talking about here. Let's go back to the example and try it out. So back to this example, we want to get the equation, right? So notice this one, it's pulled down a distance of 5 and then released. So this one, the starting position is at the bottom, right? So if I thought about drawing this out a little bit, it's starting at the bottom and then rising. Well, why is this doing a straight line? And then falling, okay? So this looks like a negative cosine pattern, right? So I'm going to use my y equals a cosine omega t, okay? And your goal is to figure out what a and omega are. A is that distance of 5, okay? Except for if you start at the bottom like this, it's -5, right? So I'm going to plug in -5 for the a. And then now all I have to do is figure out the omega. One thing I know is that the time for one complete oscillation is 4 seconds. That's the definition of a period. So the period is 4 seconds, right? So over here, I'm going to say, okay, period is 4, which means that 2 pi over omega should equal 4, right? Or if you want, if you do a little algebra, you can switch that 4 and the omega around like you've probably seen at this point. So omega is 2 pi over 4. You can almost think of this as a formula for omega right here, right? Omega is 2 pi divided by the period. And then you can reduce that, which is pi over 2. So I'm going to put pi over 2 t, and then there's my final answer. Right? There's the model for that motion, okay? For part B, it says determine the position at time t equals 1.5 seconds. So I need to plug in 1.5 for t in the above formula and calculate that to the nearest hundredth. I'll do that all in my calculator. So let's bring up the good old calculator here. Okay. One thing, if you're using your calculator for these problems, make sure you're in radian mode. So let me just check that. My mode is radians. Okay, so I'm good there. So don't do it in degrees. It'll give you the wrong answers. Now I'm going to plug in the formula, -5 cosine, and then it's pi over 2 times t. I'm going to put in pi, and then I'm going to do times the t, because those are all in the numerator, right? And then divide by 2. Okay, that's the same as pi over 2 times t. So that's a good way to put it into your calculator. And we've got our answer. To the nearest hundredths, that would be 3.54. Right? So my answer is 3.54. And that's a position, so that would be inches. Right? And if it's positive, it's above the equilibrium. So that would be the weight when the weight's up, right? If it's negative, you get it below the equilibrium. Okay. So let's jump back to the handout. Okay, the next question is find the frequency. The frequency, if you go back, there's the formulas up here, right? Frequency is omega divided by 2 pi. Right? There's a couple of ways to figure out frequency. An easier one on this one, the frequency is the reciprocal of the period. Okay, so that's a little easier on this one because you're given the period is 4. So the frequency is 1 over 4. That's it. Okay, so period and frequency are always reciprocals. And if I want I probably should give the unit of measurement on this as well, because that's one complete oscillation is 4 seconds. So this is oscillations per second. Right? Let me make sure I spell oscillations right. Okay, so that's a little more of a complete answer. All right, and then finally, let's get a graph of this. What does it look like? Let's graph it from 0 to 8. So this is actually the t-axis. I know it has x there. All right, so time is on the horizontal axis, and then position is on the y-axis. Okay, and really what I'm doing is just graphing this like from 6.3 or whatever, whenever we did that. Okay. So this is 8. So that would be 4. Right. This is 5, -5. So this one started at -5, right? And then it's going to hit here, there. Just doing the negative cosine pattern. 1 full cycle for the period of 4. Right? And then continue that. There we go. So what I'm graphing is the position of the weight at time t, right? So at any point in this on this graph, so for example, at 5 seconds, the position is right at equilibrium at 0. Okay, so let's try another example. So you have a lot of different examples, but just all kind of boils down to the same structure. Here's one about voltage. And we have the equation given to us on this one. Find the amplitude and the period. That's just really from 6.3. So the amplitude is that value out front, 3. And the period is 2 pi over omega, which is the 160 pi. Don't forget that pi in there. Right? The pi's cancel, reduce it, that's 180. That's 1/80th of a second in this case, measured in seconds. Right, so the period is always the time, right? 1/80th of a second. That's the time it takes for one complete oscillation or cycle. The frequency is always the reciprocal of the period. So just flip over 1/80th, and that's 80. So that's, I could just say cycles or oscillations per second. Okay. And then what's the voltage? Find E at the time. What's the voltage at time t equals 0.11? So there I'm going to jump to my calculator. Okay, so we have our calculator up here, and I'm going to type it in. So it's 3 cosine 160 pi times 0.11. Okay, and then we got it. And it says round this to the nearest thousandths, 3 decimals, so 0.927, and I've got it. Okay. All right, let's jump back to the handout. Okay, last thing it says on this one is to graph it, right, from 0 to 1/40th. All right, so again, this is t over here, 1/40th. So half of 1/40th is 1/80th, right? And so one full cycle happens at that point, 1/80th. And then this is a positive cosine, and goes up to a maximum of 3. The amplitude is 3. All right, so I'm going to start at 3 and then go to that quarter point, bottom out and back up, and then continue that pattern. All right, so we get 2 cycles of cosine again. That's fun. Okay, and that's what it looks like. Cool. Let's go to another one. This one says write the equation and then determine the amplitude, period, and frequency of the simple harmonic motion of a particle moving uniformly around a circle of radius 5 feet. Okay, so if you remember back, I can share that one animation again. This one has to do with that. It's still going. Oh, it's still going. Okay, so this one's really this picture right here, right? You have a point moving around a circle, and then you have a angular speed, right? How fast is that angle changing compared to the position of the point, which we're going to use as the y value, right? So the function will give you the position y value depending on the speed of that angle. Okay, so now I kind of have an idea of what we're doing. Now we can try it. Okay, so angular speed, remember, is omega. So omega is 4, right? So these are pretty cool because you just got to plug that in for omega. And then the model we're going to use is sine for these. The reason for sine is because the starting point of 0, it has a position of 0, right? Or because sine of 0 is equal to 0. That's why we're going to use sine there, right? So the equation is y equals, and the a is the radius, and then omega is 4. Okay. So almost the concept is harder on that one than than the actual finding the answer. You're just plugging in the 5 and the 4 in the right spots and you're good, right? And then you know the amplitude is 5. The period is 2 pi divided by omega, just pi over 2. And the frequency is flip that over. Right? So I can knock out those answers super fast, okay? Okay, let's try number 4. When the A key 1 octave below middle C is played on a piano, an oscilloscope produces a graph modeled by the function y equals a sine omega t. And they give us the frequency, 220 oscillations per second. Okay, let's find the value of omega. We got this because we know the formula. We have the formula from page 1. F is equal to omega divided by 2 pi. And we know F, they give it to us as 220. So I can plug 220 in for the F. And then to find omega, I'm going to multiply both sides by 2 pi. Okay, so essentially then we have 2 pi times 220. So my omega is 2 pi times 220. And in my calculator on that, I'm getting 1,382 rounded to the nearest integer. Done with that one. Okay, so that would be the value, the coefficient of the t in the function. Next, find the period of the function. Okay, so the period, probably the quickest way is knowing that the period is the reciprocal of the frequency. So period is 1 over the frequency. And the frequency is actually given in the original problem. So for that, I just need to do 1 divided by 220 and then round to 4 decimal places. So I got 0.0045. And if you were asked to find the unit of measurement, the period is always the time in these problems. So this is seconds. That's it. Okay. So that's that one. A little piano example. If you play the piano, that might interest you. Number 5, we've got one about body temperature. In a 24-hour cycle, your body temperature fluctuates. So we can model that with a function. And we're given the maximum and the minimum temperatures. Okay. And then at t equals 0, starts at 4 a.m., the time at which the person's body temperature is the lowest. So what's happening here is there's body temperature lowest, and then it's going to increase throughout the day and then decrease back to 4 a.m. So I see that as a cosine function. Okay, so I have my model, and essentially what I need to do to come up with the function is figure out what A and W are. A is the amplitude of this function. So if you think about the amplitude, it would be that distance, right, from the middle to the top, or it's half the distance from the max to the min. So A is going to equal, well, I guess absolute value of A is going to equal 99.2 minus 97.8 divided by 2. All right, and that's 1.4 divided by 2, which would be 0.7. Okay, and then I just know that A is going to be negative because of the way this problem looks, right? It's a negative cosine pattern, right? So A is going to be negative 0.7. Okay, next I need to find omega. Omega has to do with the period. So in this problem, the period is 24 because we have a 24-hour cycle. So omega is going to be 2 pi divided by 24, pi over 12. And that would be hours, right? Putting those all into the formula, I'll get my answer. So now my final answer is negative 0.7 cosine pi over 12 t. Don't forget the variable. And there's the final answer. Okay, hope that helps. You'll see some similar problems in your homework. If you have questions, you get hung up, let me know. Hope all is well. Talk to you later.